How's it going, guys? Today in this video, we're going to be going over Module 8.1, Day 3. In this video, we're going to be going over how to use the rational root theorem in real-world problems, all right? But before that, let's go over this warm-up really quickly. If you haven't tried it, I do recommend you guys to pause the video and to actually take a crack at it yourself and try to do it yourself, all right? But anyway, we're going to go ahead and get started with it. So we need to find the rational zeros of any given polynomial, and then we need to write the function in factor form. And we see that we can't actually factor this by hand. We're going to use the rational root theorem. So the first thing with the rational root theorem we need to do is we need to list out all the possible zeros of this function. All right, so all the possible zeros of this function will be all the factors of our constant term of -6 and our leading coefficient of 1. All right. But we don't actually have to worry about the leading coefficient in this case, since our leading coefficient is just 1, and the factors of 1 is just 1, and anything over 1 will just be that same number. So in this case, it's just going to be the factors of -6, so plus or minus 1, 2, 3, and 6. And you can see if you put any of these numbers over 1, it's just going to give you the same thing. That's why we don't really worry about the leading coefficient when it's just 1. Okay? So anyway, we have our possible zeros here, and now we're going to go ahead and test them. All right. So if we test with 1 first, we'll use our coefficients of our polynomial. So 1, 2, -5, and -6. Let's go ahead and do synthetic division with this polynomial. Drop down the 1, get a 1, 3. 1 times 3 is 3. -2. We also get a -2, and we get a remainder of -8. We need our remainder to be 0, so that tells me that 1 is not going to be a 0. We can cancel that out, and we can try something else. So I like to go in order: 1, -1, 2, -2, 3, -3, so on and so forth. So I'm going to try -1 next. So I have -1. My coefficients are 1, 2, -5, and -6. I'll drop down the first number, which is a 1. -1 times 1 is -1. 2 plus -1 is 1. -1 times 1 is -1. -5 plus -1 is a -6. And finally, -1 times -6 is a +6. 6 plus -6 is 0. So we get our remainder of 0. That's what we want. So what we're going to do now is rewrite this function with that factor that we just found, with that 0. So our 0 is -1, so our factor is x plus 1. Remember, with synthetic division, it goes x minus a. Our a is -1. X minus -1 gives us an x plus 1. Okay? So we have x plus 1, and we're going to multiply that with our quotient we found with that factor. So x plus 1 times x squared plus x minus 6. And we see x squared plus x minus 6 can still be factored out. So we're going to factor that out some more. We need factors of -6 that add up to give us a +1, our c value that adds up to our b value. In this case, it'll be +3 and -2. And that's what our factor is going to be. And you can use the box method or whatever other method you like, as long as you get the right factor form. It's okay, but that's what you get when you factor it out. So our zeros are going to be -1, -3, and +2. To find the factors, to find the zeros, you set each factor to 0 and solve for x. So x plus 1, you set that equal to 0, you get -1. X plus 3, set that equal to 0, you get -3. X minus 2, set that equal to 0, you get +2. In our factored form is what we have at the end over there, x plus 1 times x plus 3 times x minus 2. So that's our factored form, and those are our zeros, okay? So that's the warm-up, and let's keep going and get started with the notes for the day. So finding the zeros of a polynomial is the same as finding the solution, or let's get the solutions, which are also known as a root. Okay? So solutions, roots, x-intercepts, zeros, whatever, they're all, for the most part, pretty interchangeable. They all refer to basically the same thing, okay? So let's go ahead and start an actual problem. We're told to use the rational root theorem to solve each of the following problems. So for number 1, we're told a pen company is designing a gift container for their new premium pen. The marketing department has designed a pyramidal box with a rectangular base. The base width is 1 inch shorter than its base length, and the height is 3 inches taller than 3 times the base length. Those are both pretty important, so I'm going to underline them. And next, we're told the volume of the box must be 6 cubic inches. And we're ultimately going to be solving for the dimensions of the box. So first thing we need to do is figure out what x is going to be. All right, if I look at the two first things that I underlined, we're told the width is 1 inch shorter than its base length, and the height is 3 inches taller than 3 times the base length. They're both being explained in terms of the length, right? So they're both being, if everything's being told in terms of the length, that means we want our x to be the length, right? We want everything in terms of x, so we want everything being told in length, right? That's what it's being told as, so that's why we set x equal to the length. So next we're going to write what we know. Our length we said is x. Our width we're told is 1 inch shorter than its base length, so 1 less than x. And then we're also told the height is 3 inches taller than 3 times the base length, or 3x plus 3. 3 inches taller than 3 times the length. And last, we're told the volume of the box must be 6 cubic inches, or the volume equals 6. All right? So what we're going to do now is we're going to substitute this all into the volume formula, and we're going to get our own standard form of an equation so we can actually factor this out and figure out what our x should be. All right? So our volume, we're giving you the formula right here, is B equals 1/3 B times H. So our volume is 6, and that should equal 1/3 times our big B, which is like the actual base of the whole thing, which will be length times width. So x times x minus 1, and our height, which is 3x plus 3. All right, so in other words, just 1/3 times length times width times height. So what I'm going to do now is I'm going to minus the 6 over, and then I'm going to multiply x and x minus 1. So I get 0 equals 1/3 times x squared minus x times 3x plus 3 minus 6. All right. Remember, standard form, you have to be the equation has to be set equal to 0. If it's not set equal to 0, it's not going to work. You can't use the rational root theorem. So I moved over to 6, and now I'm going to multiply x squared minus x with 3x plus 3. So 0 equals 1/3. I end up getting 3x cubed plus 3x squared minus 3x squared minus 3x, all minus 6. So I'm just distributing everything out. Next, I'm going to add like terms. I can see 3x squared and negative 3x end up canceling. And I can also see if I distribute that 1/3 inside the parentheses, all the 3's go away, right? 3 times 1/3 just gives you a 1, so the 3's all go away. So I get 0 equals 3x cubed minus 3x. Oh, sorry, it's not supposed to be 3x squared. It's supposed to be x cubed minus x minus 6. Sorry about that. All right, because you distribute that 1/3 inside the parentheses, all the 3's go away. At the same time, 3x squared and negative 3x squared cancel each other out. We're left with 0 equals x cubed minus x minus 6. So this right here is our standard form of the equation. And what we're going to do now is we're going to list all our possible rational zeros. So remember, all our possible rational zeros will be plus or minus the factors of the constant, which is 6, all over the factors of the leading coefficient, which is 1. But since our leading coefficient is 1, all our possible zeros will just be the factors of 6. So as we can see, if we put any of these factors over here, over 1, we'll get the same thing, so it doesn't really matter. All right, the leading coefficient doesn't really affect the possible rational zeros in this case. So next, we're going to test all our possible zeros. But before we actually do that, we should actually look at all our possible rational zeros and kind of start canceling stuff out that doesn't really work with our problem, right? So we're told our length equals x, and we can't have a negative length value, right? It doesn't make sense to have something negative inches long. So that means we can cross out every single negative value in this problem because it's not going to help us. It doesn't make sense to have a negative length. Next, we can cross out our 1 because our width is x minus 1. If you plugged in x equals 1 into the width, you get a width of 0, and that also doesn't make any sense, right? You can't have a width of 0 and call yourself a 3D object. It doesn't work. So right away, we can cancel out all the negative terms, and we can cancel out the 1. So now we're going to go ahead and test our possible zeros, but we're going to do it starting with the 2. So we'll start with 2, and when we do, we have our coefficients right here above it, x cubed minus x minus 6. So it's 1. We don't have an x squared term, so we put a 0. Minus 1 minus 6. Do our synthetic division. We'll drop the 1. 2 times 1 is 2. 0 plus 2 is 2. 2 times 2 is 4. Negative 1. Sorry about that. Negative 1 plus 4 is 3. 2 times 3 is 6. And we get a remainder of 0. So that means 2 is a possible 0 for this problem. So now we're going to factor it out. When our a value is 2, our factor is x minus 2. And our quotient is what we multiplied it with. So x squared plus 2x plus 3. And we need to see if we can factor this out anymore. We want to completely factor it out if we can. But we can see x squared plus 2x plus 3. It doesn't really factor out anymore since there's no factors of 3 that add up to give you a positive 2. So this is completely factored out as it is. We can stop right here. And we can see that our only rational 0 in this problem is positive 2. So that's what our length is going to be. We can plug in our x equals 2 into our length width height that we have in letter A. So our length gives us a 2. Our width is 2 minus 1, or just 1. And then we plug in x equals 2 into our height. We get 3 times 2, which is 6. And 6 plus 3, which is 9. All right? And what we can do also to double check our answer is that we told you guys that volume equals 1/3 times base times height. We can plug everything in and see what we get. We said our volume has to be 6, and that should equal 1/3 times 2, 1, and 9. So we multiply everything out. 6 equals 1/3. 2 times 1 times 9 is 18. And 1/3 of 18 is 6. That means we're correct. Our answer works. All right. For number 2, I want you guys to actually pause the video and try it yourself. If you need to rewatch what I did, this problem, rewind the video, watch it again. But please pause the video, and then I'll post the answer in a bit. You can double check the work we got. All right. All right. So here's number 2. For number 2, we need our x to be equal to the length, and that's because everything's being told in terms of the length. So we're just going to let x equal length. It makes it the easiest. Next, our length is going to be x. Our width is going to be x minus 2, since the width is 2 inches shorter than the length. And the height is x plus 3, since the height is 3 inches longer than the length. And our volume, we're told, is 56. Next, we're going to put it into our volume formula. Since it's a rectangular prism, it's only length times width times height. The only time you'd ever multiply with 1/3 is if you have some kind of triangular or pyramidal shape. In this case, we don't. We just have a rectangular div, so it's just length times width times height. So x times x minus 2 times x plus 3 equals 56. If you distribute everything out and add like terms, all that good stuff, you put it in standard form, you should get x cubed plus x squared minus 6x minus 56 equals 0. Next, we're going to list out all our possible rational zeros. Our leading coefficient is 1, so it's just going to be all the factors of negative 56. So 1, 2, 4, 7, 8, 14, 28, and 56. But like the previous slide, we were going to go ahead and test our zeros. There's going to be a few things we can cancel out right away. We can't have a negative length, so we can't have any negative x values. We can cross out all the negatives. And at the same time, we can cross out 1, since our width, if you plug in 1 into our width, would get a negative 1. That doesn't make any sense. And same thing with 2. If you plugged in a 2 into our width, we'd get a width of 0. That doesn't make any sense either. So we can go ahead and cross out all the negatives and the 1 and the 2. All right? So we can go ahead and start checking. If we did, we start with the 4. We plug in our 4 into our synthetic division. We solve it out. We get a remainder of 0, which is what we wanted. So that means our factor will be x minus 4, the opposite of our a value here. So x minus 4 times our quotient down below here, x squared plus 5x plus 14. X squared plus 5x plus 14 doesn't factor out anymore. There's no factors of 14 that add up to give you 5. So we're done factoring over here. And now we can list our actual rational zeros, which just happens to be 4. So we plug in our 4 into our terms that are 8 under our a, so our length, width, and height. If we do, we get our length to be 4, our width to be 2, and our height to be 7. And you can double check yourself here as well. If you multiply 4 times 2 times 7, you should get the volume of 56 that we said the thing should weigh. 4 times 2 is 8. 8 times 7 is 56. So that means our answer is correct, and we're good to go. All right, and that's all the notes for the day, guys. Hopefully this helped.